Warm welcome to all. We are going to discuss about mechanical translational system. Mechanical system are classified into two categories of one mechanical translational system. Another one is mechanical rotational system. Mechanical translational system are related to force and translational motion. Mechanical rotational systems are related to torque and angular motion. Mechanical translational system Mechanical translational system, the motion is along a straight line. The variable of the system are displacement, velocity, and acceleration. The mass, damper, and spring are the basic characteristics elements of translational mechanical system. There are three restricting or opposing force encountered in the translational mechanical system, which oppose the motion of the mechanical system due to external applied force. The various list of the symbols used in mechanical translational systems: x equal to displacement, v equal to velocity, a dv by dt equal to d square x divided by dt square equal to acceleration, f equal to applied force, fm opposing force offered by mass, Fk opposing force offered by elasticity, Fb opposing force offered by the friction, M symbol of mass, K stiffness of the spring, B viscous friction. The applied force F, the opposing force of the various basics elements are: first one is mass. Okay, mass, consider the ideal mass element. M is the symbol of mass, x is the displacement, F is applied force, Fm equal to opposing force due to mass. Opposing force due to mass is directly proportional to d square x dt square, or Fm equal to m into d square x divided by dt square. This formula is opposing force due to mass. Next, opposing force due to dash part. B is symbol of dash part. Fb equal to opposing force due to friction or dash part. Fb directly proportional to dx divided by dt, or Fb equal to b into dx divided by dt. This formula is opposing force due to dash part. Next, the above formula, one end fixed, another one end is open. Next, one two ends are open. This type of the dashboard, the applied the opposing force due to dashboard directly proportional to d by dt into x1 minus x2. Then f equal to, or fb equal to b into d del by dt x1 minus x2. This is opposing force due to dashboard. Two ends are open. Next, opposing force due to spring. The opposing force Fk equal to opposing force due to spring. The opposing force due to spring directly proportional to x. X is the displacement of the spring. Yeah, so the opposing force due to spring is equal to k into x. Then two ends are open means opposing force due to spring Fk equal to k into x1 minus x2. Then we are going to discuss about one problem based on mechanical translational system. All of note the problem. First problem is: write the differential equation governing the mechanical system shown in figure and determine the transfer function. In this problem, we have two mass m1 and m2. We have find determine the transfer function of the mechanical translational system. Solution: uh, we have find the transfer function x of s divided by f of s. First, note the first mass m1. This m1 mass displacement is x1. Then opposing force due to first mass is f m1 FB1, FB, FK1, and FK. Fm1 means opposing force due to mass m1. Fb1 means uh, opposing force due to dash part b1. Next, Fb means opposing force due to dash part b. Next, Fk means opposing force due to spring. These are connected in first mass. So the formula is this in this mass there is no applied force. So applied force equal to zero. Opposing force by Newton's second law. Applied force equal to opposing force. In this mass, applied force equal to zero. Opposing force are Fm1 plus Fb1 plus Fb plus Fk1 plus Fk. So apply the opposing force formula. Fm1 is m1 into d square x1 divided by dt square. Fb1 equal to b1 into dx1 divided by dt. Next, Fb equal to b into dx1 minus x divided by dt. Next, Fk1 is k1 into x1. Next, k is k into x1 minus x. In by Newton's second law, applied force equal to opposing force. Next step, move to on taking Laplace transform of above equation. Taking Laplace transform of above equation, then m1 into s square into x1 of s. mm, a Laplace transform of d square x1 divided by dt square is equal to s square into x1 of s. So we have substitute the formula m1 into s square into x1 of s. Then Laplace transform of dx1 divided by dt equal to s into x1 of s. So b1 into s1 s into x1 of s. Next, b s into x1 of s minus x of s. Next, Laplace transform of x1 equal to x1 of s. So k1 into x1 of s plus k into x1 of s minus x of s. This is Laplace transform of the above equation. Next, this equation split into two term, x1 of s and x of s. Then negative term moved into right hand side. So x1 of s m1 s square plus b1 plus b into s plus k1 plus k equal to x of s into bs plus k. Next, uh, bs plus k moved into left side. So finally we get x1 of s equal to x of s into bs plus k divided by m1 s square plus b into s plus k1 plus k. Next, moved into second mass m2. In this mass displacement x, then applied force equal to f of t, then opposing force f m2, fb2, fb, fk. So by Newton's second law, applied force equal to opposing force. Applied force F of t equal to Fm2 plus Fb2 plus Fb plus Fk. Then substitute the opposing force formula for Fm2, Fb2, Fb and Fk. Then finally we get m2 d square x divided by dt square plus b2 into dx divided by dt plus b into dx minus x1 divided by dt plus k into x minus x1 equal to f of t. So then find the Laplace transform of the above equation. We get m2 into s square x of s plus b2 into s into x of s plus b x of s minus x1 of s plus k into x of s minus x1 of s equal to f of s. Next, split into two form x of s and x1 of s. Next, move to negative in right hand side. So finally we get x of s into m1 s square plus b1 plus b into s plus k minus x1 of s bs plus k equal to f of s. Next, uh, x1 of us is substitute to the above equation. Finally, we get x of s into m2 s square plus b2 plus b plus into s plus k equal to, sorry, minus x of s bs plus k whole square divided by m1 s square plus b1 plus bs plus k1 plus k equal to f of s. Then cross multiply by to the m1 s square plus b1 plus bs plus k1 plus k. Then we get x of s into m1 s square plus b2 plus b s plus k into m1 s square plus b1 plus b into s plus k1 plus k minus bs plus k whole square divided by m1 s square plus b1 plus b into s plus k1 plus k equal to f of s. Next, f of s move to left hand side. We get final equation of transfer function x of s divided by f of s equal to m1 s square plus b1 plus b into s plus k1 plus k divided by m1 s square plus b1 plus b into s plus k1 into k into m2 s square plus b2 plus bs plus k minus bs plus k whole square. This is the transfer function of the above mechanical translational system. This is final answer of the above problem. Then solve the another one problem. This problem solve like the above problem. In this problem, determine the transfer function y2 of s divided by f of s of the system shown in figure. And this diagram, two mass m1 and m2, displacement and y1 and y2. Y1 is the displacement of m1, y2 is the displacement of m2. Same, that first note that first mass, in this first mass applied torque f of t, then, sorry, applied force f of t, and opposing force fm1 and fk1 fb and fk2 by Newton's second law. Applied force equal to opposing force, applied force equal to f of t. Therefore, f of t equal to fm1 fb plus fk1 plus fk2. Then applying the opposing force formula for fm1 fb fk and fk2. So finally we get m1 d square y1 divided by dt square plus m dy1 divided by dt plus k1 y1 plus k2 y2 minus, sorry, k2 y1 minus y2 equal to f of t. By taking Laplace transform of the above equation, m1 s square into y1 of s plus bs y1 of s plus k1 y1 of s plus k2 y1 of s minus y2 of s equal to f of s. Y1 of s m1 s square plus bs plus k1 plus k2 minus y2 of s k2 equal to f of s. This is differential equation of the first mass. Next, note that second mass, opposing force is fm2 and fk2. In this mass, displacement y2, but in this mass there is no applied force. So, by Newton's law, applied force equal to opposing force. In this mass, applied force equal to 0. Therefore, F m2 plus fk2 equal to 0. By applying the opposing force due to the m2 and k2, in this substitute in this equation, m square d square, sorry, m2 into d square y2 divided by dt square plus k2 into y2 minus y1 equal to 0. On taking Laplace transform of the above equation, we get m2 s square y2 of us plus k2 into y2 of us minus y1 of us equal to 0. Next, substitute the sorry split the two form y2 of us and y1 of us, then finally get y1 of us equal to y2 of us into m2 s square plus k2 divided by k2. Next, substituting for y1 of us from the equation number 3 in equation number 2, we get y2 of us into m2 s square plus k2 divided by k2 into m1 s square plus bs plus k1 plus k2 minus y2 of us k2 equal to f of us. Next, just multiply into the y2 of us term. Next, finally, f of s move to the left hand side. We get transfer function of the above canonical rotational system. Y2 of s divided by f of s equal to k2 divided by m1 s square plus bs plus k1 plus k2 into m2 s square plus k2 minus k2 square. This is the final answer of the above problem. This equation is the transfer function of the mechanical translational system. Then we are moved to mechanical rotational system. The model of rotational mechanical system can be obtained by using three elements: moment of inertia, mass, dashpot with rotational frictional coefficient, and spring with stiffness. Mechanical, one second. Mechanical rotational system is basics. Three elements are moment of inertia, dashpot, and spring. Rotational system are related to torque and angular motion. The symbol of the mechanical rotational system are theta is angular displacement, d theta divided by dt equal to angular velocity, d square divided by d square theta divided by dt square equal to angular acceleration, t equal to applied torque, j equal to moment of inertia, b equal to rotational frictional coefficient, k equal to stiffness of spring. The basic three elements of mechanical rotational system are: first one is J, moment of inertia; next B, dashpot; and K, spring. In this formula, applied torque T, opposing torque due to moment of inertia is Tj, and opposing torque due to dashpot is Tp, and opposing torque due to spring is Tk. In this method, opposing torque due to moment of inertia is Tj equal to J into d square theta divided by dt square. Applied torque T and opposing torque due to moment of inertia of the body is equal to Tj. So Tj is directly proportional to d square theta divided by dt square. So Newton's second law, opposing torque due to moment of inertia equal to J into d square theta divided by dt square. Next, uh, dashpot, applied torque of dashpot equal to T. Uh, Next, opposing torque due to friction is equal to TB. So TB is directly proportional to T theta divided by dt. Theta is the angular displacement of the dashpot. So by Newton's second law, opposing torque due to dash part with one end fixed means TB equal to B into d theta divided by dt. Next, two ends are open means applied torque due to dash part is equal to TB directly proportional to d theta 1 minus theta 2 divided by dt. So, by Newton's second law, opposing torque due to dash part 2 ends open means TB equal to B into d theta 1 minus theta 2 divided by dt. Next, opposing torque due to spring is equal to Tk. Applied torque is equal to T. Therefore, Tk is directly proportional to theta. Theta is the displacement of the angular displacement of the spring. So, Tk directly proportional to theta. Uh, so, by Newton's second law, opposing torque due to spring Tk equal to k d theta. In this spring, one end are fixed, two ends are open means opposing torque due to spring dk directly proportional to theta 1 minus theta 2. So two ends are open means opposing torque due to spring two ends are open equal to k into theta 1 minus theta 2. Next, one problem of mechanical rotational system. In this problem, write the differential equation governing the mechanical rotational system shown in figure 1 and determine the transfer function of theta s divided by f of s. In this figure, two moment of inertia J1 and J2. In this problem, apply torque theta and theta 1 is the angular displacement of J1 and theta is the angular displacement of J2. J1 and J2 is connected between one spring K and another one dash part B12. First note that uh, first moment of inertia J1. In this moment of inertia, apply torque T and opposing torque are Tj1, Tb12 and Tk. In this moment of inertia, angular displacement is theta 1. By Newton's second law, applied torque is equal to opposing torque. In this moment of inertia, applied torque equal to T. Therefore, T equal to Tj1 TB12 TK. So TJ1 plus TB12 plus TK equal to T. So apply the opposing force due to moment of inertia, dash part and spring in above equation. So J1 into d square theta 1 divided by dt square plus B12 into d theta 1 minus theta divided by dt plus k into theta 1 minus theta equal to t. Then on taking Laplace transform of the above equation, Laplace transform of uh, d square theta 1 divided by dt square is equal to s square into theta 1 of s. Next, Laplace transform of uh, d theta divided by dt equal to s into theta of s. Next, substitute this formula in above equation. Finally we get j1 into s square theta 1 of s plus s into b12 theta 1 of s minus theta of s plus k into theta 1 of s minus k into theta of s equal to t of s. Next, split into two equation theta 1 of s form and theta s form. Next, note that second moment of inertia. In this moment of inertia, there is no applied torque, only the opposing torque. The opposing torque are Tj2 plus Tb12 plus T Tb plus Tk. By Newton's second law, applied torque is equal to opposing torque. In this moment of inertia, there is no applied torque. So T J2 plus T B12 plus T B plus Tk equal to 0 because there is no applied torque. Then substitute the opposing torque formula in this above equation. Opposing torque due to moment of inertia t j2 equal to j2 into t square theta divided by dt square, and same db1 equal to b12 into d theta 1 minus theta 2 divided by dt, and db equal to b into d theta divided by dt, and tk equal to k into theta minus theta 1. Substitute this formula into the Newton's second law equation. Finally, we get j2 into d square theta divided by dt square plus b12 into d theta minus theta 1 divided by dt plus b into d theta divided by dt plus k into theta minus theta 1 equal to 0. Next, rearrange this equation. We get j2 equal to d square theta divided by dt square minus b12 d theta 1 divided by dt plus d theta divided by dt b12 plus b plus k theta minus k theta 1 equal to 0. On taking the Laplace transform of the above equation, we get j2 into s square theta of s minus b12 s theta 1 of s plus s into theta of s into b12 plus b plus k into theta of s minus k into theta 1 of s equal to 0. Just rearrange this equation. Finally, we get theta 1 of s equal to s square j2 plus s into b12 plus b plus k divided by s into b12 plus k into theta of s. Substituting the theta 2 of s from the equation number 2 in equation number 1, we get j1 s square plus s into bk2 plus k into j2 s square plus s into theta, sorry, s into bs2 plus b plus k into theta of s divided by s b12 plus k minus s into b12 plus k into theta of s equal to t of s. Next, t of s is moved into left hand side. Finally, we get transfer function of the above mechanical rotational system, or theta of s divided by t of s equal to s into b12 plus k divided by j1 s2 plus s into b12 plus k into j2 in j2 into s square plus s into b12 minus b plus k minus s into b12 plus k whole square. This is the final answer. This equation is the Laplace transform of transfer function of the above mechanical rotational system. Another one problem. This is very simple problem. Example number 1.5. Write the differential equations governing the mechanical rotational system shown in figure. Obtain the transfer function of the system. In this problem, two moment of inertia J1 and J2. In this mechanical rotational system, applied torque is T, and displacement is theta and theta 1. J1 and J2 is connected between K2. K is the spring of the moment of inertia. Next, same like that, in this problem, find the uh, transfer function theta of s divided by t of s. First, note that first moment of inertia J1. In this problem, first moment of inertia, uh, there is one applied torque T and opposing torque T J1 and Tk, and displacement theta 1. By Newton's second law, applied torque equal to opposing torque, correct? So T equal to Tj1 plus Tk. T is the applied torque, and Tj1 and Tk is opposing torque due to the first moment of inertia. We are now that opposing torque due to moment of inertia Tj1 equal to J1 into d square theta 1 divided by dt square, and like that same opposing torque due to spring tk equal to k into theta 1 of theta 1 minus theta. In this formula substitute to the Newton second law equation, so we get j1 into d square theta 1 divided by dt square plus k into theta 1 minus theta equal to t. Correct. Next, on taking the Laplace transform of the above equation, we are all know that Laplace transform of d square theta 1 divided by dt square equal to s square into theta 1 of s. Correct. Then Laplace transform of theta 1 equal to theta 1 of s. Correct. Next, this for Laplace transform formula substitute the above equation, we get j1 s square theta 1 of s plus k into theta 1 of s minus k into theta of s equal to t of s. Next, substitute the theta 1 of s and theta 2 of s means j1 s square plus k into theta 1 of s minus k into theta of s equal to t of s. This is the equation number 2. Next, note that second moment of inertia j2. In this moment of inertia, there is no applied torque. Okay, so applied torque equal to 0. By Newton's second law, applied torque equal to opposing torque. In this moment of inertia, there is three opposing torque. These opposing torques are tj2 tb plus tk. These are opposing torque due to second moment of inertia. So by Newton's second law, applied torque equal to opposing torque. In this moment of inertia, applied torque is equal to 0. Therefore, tj2 plus tb plus tk equal to 0. We are all know that opposing torque due to the moment of inertia j2 tj2 equal to j2 into d square theta divided by dt square, and opposing torque due to dash part tb equal to b into d theta divided by dt, and opposing torque due to spring tk equal to k into theta minus theta 1. This opposing torque formula is substitute the Newton second law equation, so we get j2 into d square theta divided by dt square plus b into d theta divided by dt plus k into theta minus theta 1 equal to 0. Next, on taking Laplace transform of the above equation, j square, sorry, j2 into s square into theta of s plus b into s into theta of s plus k into theta of s minus k into theta of 1 is equal to 0. Okay, then rearrange this equation j1 s square plus k into j2 s square plus ds plus k minus k square divided by k into theta of s equal to t of s. Then t of s moved into left hand side, theta of s divided by t of s equal to k divided by j1 s square plus k into j2 s square plus bs plus k minus k square. This is the transfer function of above equation, sorry, transfer function of the above mechanical rotational system. This is final answer of the our problem. Here all not transfer function means Laplace transform of output to the Laplace transform of input with zero initial condition. So in this problem, Laplace transform of output is theta of s and Laplace transform of input is t of s. So Laplace transform of output to the Laplace transform of input with zero initial condition. In this problem, theta of f theta of s divided by t of s is the Laplace transfer function of the mechanical rotational system. So the final answer is theta of s divided by t of s equal to k divided by j1 s square plus k into j2 s square plus bs plus k minus k square. This is final answer. Okay, isn't it? This is very simple problem of mechanical translational system and mechanical rotational system. In these two categories, we have find the lab transfer function of the mechanical translational and rotational system. Thank you so much. Thank you very much, students. Thank you.